At the beginning of this course, we learned about mixtures. We learned that a heterogeneous mixture is a mixture of two or more substances that's not uniform in composition. You can see the different phases present. We also learned that a homogeneous mixture is a mixture of two or more substances that does look uniform throughout. Another name for a homogeneous mixture is a solution. In this photo, we have a glass of Kool-Aid, and in it, we're dissolving some sugar. Sugar is soluble. That means it's capable of being dissolved. Solutions are made of a couple of different components. First, we have the solute. That's the substance that's being dissolved in solution. Next, we have the solvent. This is where the solute is being dissolved, or the dissolving medium. In a solution, the dissolved solute particles are very small. That means that if you tried to filter out this solution, both the solute particles and the solvent would pass through the filter paper. Solutions can be liquids, but they can also be solids. 14 and 18 karat gold both have other metals mixed in. This makes them stronger and makes the jewelry a little bit less expensive. A mixture of metals is known as an alloy. Solutions can also be gases. Our atmosphere is a mixture of gases, also a solution. When solute particles are really large, they won't stay suspended in the solution. Eventually, they just all settle out to the bottom. This type of mixture is a suspension. This is an example of a suspension. It's flour dissolved in water. And if you filtered out this mixture, you'd be able to separate the flour from the water. When the solute particles are in between those of a solution and a suspension, like the foam in this cappuccino, then what we have is a colloid. Colloids, or colloidal dispersions, where the solute, in this case a gas, would stay suspended in the solvent. Colloids are also known as emulsions or foams. You can differentiate between a solution, a colloid, or suspension by using a flashlight. If you shine a flashlight through a mixture where the solute particles are a little bit larger, for example, in a colloid or a suspension, then those larger sized particles will reflect the beam of light, and so you'll actually see it passing through the mixture. This is known as the Tyndall effect. You won't see the Tyndall effect in a true solution because the particle size of the solute is so small. Both sugar and salts are soluble in water, but once they dissolve, they behave very differently from each other. Table sugar, or sucrose, is made of carbon, hydrogen, and oxygen. It's a molecular compound because it's made from all nonmetals that are covalently bonded together. Since sucrose is a molecular compound, when it dissolves in water, it still will maintain its identity of being discrete sucrose molecules. So these molecules actually stay intact together while dissolved in solution. Sodium chloride, or table salt, is composed of a metal, sodium, and a nonmetal, chlorine. And so the metal and nonmetal are ionically bonded together. When table salt, sodium chloride, is dissolved in water, the sodium ions and the chloride ions are separated by the water molecules. When we have a solution that contains when we have a solution with ions in it, it's known as an electrolyte, or a solution that will conduct electrical current. Salts, or ionic compounds, as well as strong acids and strong bases, all form ions in solutions of water, and therefore make good electrolytes. You've probably heard that Gatorade contains electrolytes. And if you take a look at the ingredient list on the label, you'll find a few ionic compounds listed there. Non-electrolytes are solutions that don't conduct an electric current. So why is water able to take an ionic compound like sodium chloride and pull those ions apart? Well, we know that water is a very polar molecule and that the oxygen end of it has a partial negative charge on it and the hydrogen end has a partial positive charge on it. It's that negatively charged oxygen end that has a nice attraction for the positively charged sodium ions. And that slight positive hydrogen end will be attracted to the negatively charged chloride ions. And it's enough of an attraction to overcome the attraction that these two ions have for each other. And so it's able to separate them and surround each ion with water molecules. So what we end up with is these ions floating around in our solution. There are a few things that we'll talk about that have to do with how well or how quickly a solute will dissolve in a solvent. The first factor is surface area. If you put a sugar cube into your tea, it's only these molecules that are on the surface here that are going to be able to dissolve. If we were to smash this sugar cube up into a bajillion little pieces, now we've got a bajillion times more surface area to come in contact with the solvent. And so our solute would dissolve much faster if we could increase the surface area. Agitating the solution, or stirring, or shaking, also helps the solution process along by increasing the amount of contact that the solvent has with the solute particles. And the third factor is temperature. It's a lot easier to get sugar dissolved in hot tea than it is in cold tea. The hotter the temperature of the solvent, the more kinetic energy it contains, since the molecules are moving faster. And the faster those molecules move, the faster the collisions will be between solute and solvent particles, speeding up the solution process. Some substances are more soluble than others. Solubility of a substance is the amount of that substance that's needed to form a saturated solution with a specific amount of solvent at a specific temperature. And so we have a graph here depicting a bunch of ionic compounds and their solubilities. Notice the units of expressing solubility are grams of the salt, grams of the ionic compound, per 100 grams of solvent, which is water in this instance. And you can see how most of the compounds have an increased solubility at a higher temperature, but that's not always going to be the case. Remember, though, that solubility of a substance refers to the amount of the substance that's going to form the saturated solution. It doesn't have anything to do with the rate of solubility or how fast a substance will dissolve. So when we say that a solution is saturated, that means that the solvent contains the maximum amount of dissolved solute possible. And so if a solution is saturated, and you keep adding more solute to it, the excess that's unable to be dissolved is just going to sit at the bottom of the container. And although it looks like it's just sitting there, it's actually forming what we call a dynamic equilibrium. And on the molecular level, what's happening is that simultaneously some of that excess solute is going to dissolve, and as some of it dissolves, some of the dissolved solute is going to recrystallize and become a solid and go to the bottom again. And so this is just a continuous cycle. That's why we call it a dynamic equilibrium. The dissolving and the recrystallizing is occurring at the same rate. An unsaturated solution contains less solute than a saturated solution would under the same conditions. For example, according to our graph, at 10 degrees Celsius, let's take a look at the solubility of sodium nitrate. At 10 degrees Celsius, a saturated solution would contain 80 grams of sodium nitrate for 100 grams of water. that would be a saturated solution. So at 10 degrees Celsius then, if we had a solution of sodium nitrate that contained, let's say 20 grams of sodium nitrate and 100 grams of water, that solution would be unsaturated. That 100 grams of water could hold an additional 60 grams of our solute. A supersaturated solution contains more dissolved solute than a saturated solution would under the same conditions. In other words, a supersaturated solution is going to contain more dissolved solute than theoretically should be possible. For example, we'll take a look at our same example as we used before. At 10 degrees Celsius, the saturation of sodium nitrate would be 80 grams in 100 grams of water. Well, if we were at 10 degrees Celsius and we managed to get 100 grams of sodium nitrate dissolved in that 100 grams of water, then we would have a supersaturated solution. However, it's really difficult to create a supersaturated solution, and most compounds won't do that for you. You end up having to heat the solution up first to get more solute to dissolve, and then let it slowly cool back down to its original temperature. But a supersaturated solution is highly unstable. So once you've cooled it down, if you added just one tiny little crystal more of your solute to the solution, it would cause the entire solution to crystallize out like you see here. And we'll do this demo in class, and there's also a video on the website. So supersaturated solutions can be difficult to create, and they're very unstable.